We're going to go from a D latch to an edge triggered flip-flop. Perhaps we'll see how the edges happen here in a second. Alright, so making D flip-flop, this is a latch. Let's look at how this works for a second. Is this positive or negative latch? Well, what do we mean by a positive or negative latch? A latch has two states. We have transparent. Another name for this state is tracking mode. Okay, and then also hold mode, or maybe latch mode, but I never use that word. All right, so transparent and track. If this is in track mode, we have a switch here. I'm going to call this node A, and we'll use that later. In transparent mode, if that means that there is a switch connection between A and X, and the switch is closed. To get that switch to close, phi has to be high, which means the N MOS is on, the P MOS is on. Both are on at the same time because we're fed with this clock signal, or control signal is opposite. If clock is high, clock bar is low. Both of these transistors are on. We have a switch across here. In hold mode, phi is low. Both transistors are off. We have, this is track, hold mode, A and X are disconnected. Now we could redraw this. This inverter here is just a buffer. When we say buffer, it's an inverting buffer, but to be a little more precise, but it just isolates the node A from whatever noise might be coming in from the inside, or from the outside world. And that's always a good idea, but it does take up chip area and adds to our delays, so it's always a trade-off. Another thing, so we can take this out, perhaps. This is a cross-coupled pair, or a positive feedback. This is what holds node X. We could take these out and then rely only on the charge of this capacitor. So we could take this whole circuit and turn it into D, our transmission gate, phi and phi bar, have node X, and here at node X we have an implied capacitor. I'll call this C hold. Okay. This capacitance is just at this node anyway, and we're relying on this capacitance for a dynamic latch. And when we add this, it turns into a static latch. Because it holds there, we can stay. There's this feedback loop does this. What is this? This is a tri-state inverter. We did this in another lecture or talk. You can really also view this as a inverter followed by a transmission gate. Notice how we have this here. Here's what we have to be careful with. I'm going to put a bubble here. Okay, so on the bubble is phi. On the bubble, this one is phi bar. But please notice that the NMOS is attached to phi. I'll use a little highlighter. NMOS is attached to phi for the other one, which means it's off then on. Be careful of that. This connection sets the positivity of this. The reason again that we have the switch on this node is so that these two inverters, or whatever is driving this, don't fight when this switch is on. If this is on, then this one is off and it's disconnected. That's a good thing. All right, so when we say positive, positive latch, or positive or negative is like where's the clock signal. So phi, oh my goodness, phi is high. I'm going to erase that so you can't see my mistake. Okay, phi is high to track. If phi is, or clock here is high in track mode, that means it's positive. Alright, so this is a positive latch. Next up, we're going to start to make a master-slave flip-flop. I'm not going to show you what's below there yet. A master-slave flip-flop is just 2 latches in cascade. That's not series, but it's one followed by the other. The very simplest version, we could use this. Here's our transmission gate. Be careful here. Here's our implied capacitor, or capacitance. And here is, I guess this would be Q. There's no inversion in here. Now watch. Let's see. We're going to make a positive edge triggered flip-flop here. So it's a negative latch followed by a positive latch. To make a negative latch here, I want this one is negative and this one is positive. I need to have my PMOSs. This is a negative latch, so when the clock is low, this is on. So this is phi bar, and this is just phi. Be careful of this. This one is opposite, so when clock is high, this is transparent, so this is phi, and this is phi bar. Be careful of these connections. They are opposite. They are opposite. They are opposite. Okay? Our whole capacitor here. Now, we'd like to have buffers here. We like to add other features so that we don't have to hold charge on a capacitor. Would be a dynamic flip-flop. Clearly, it only uses 4 transistors. It takes a very small amount of area, but it has lots of problems with it. You have to do it just right, and the physical layout makes a difference. So let's convert that. Here's one latch. Here's another latch. We see that phi is attached to the PMOS, so this is a negative latch. Phi is attached to the NMOS, so when phi is high, this is on, so this is a positive latch. And we have a buffer. We also have a buffer, and a buffer here, just to keep our signals nice and square. Because we have 3 inverters that go through the system, we end up with Q bar at the output, which but it's not a big deal. So next up, we're going to take that, extend this. Remember that we have a buffer here. We have this cross-coupled pair, or this hold circuit. We can combine all of these together. Our positive circuit. Do you notice that these 2 signals are opposite? Okay, remember this is the negative latch. This is the positive latch. Okay, there's my pen. This is a negative latch. Phi is attached to the PMOS transistor. Phi bar is here, so when the clock is low, this is on. When this one is on, I want this to be off, so this is opposite. So phi bar is attached to the PMOS. Phi is attached to the NMOS in this one. Phi bar is attached to the NMOS in that one. So we have a positive latch, so phi is attached to the NMOS, and then phi bar is attached to the NMOS over here because these are opposite. These 2 are opposite. But if you look, this one is on and this one is on at the same time. These go together. and these two go together. If you look at the clock phases, you have to get the clock phases correct. We have a buffer at the input. We have a I don't know the name. All right, so I'm not coming up with the name. It's been a long week. All right, so we're going to hold this here in this loop. We have another hold circuit here. This is a buffer, because if we want our Q bar to come out of this circuit because of all of our inversions here, because it's convenient for the rest, we don't want to attach external stuff to this node. Okay, so we're going to use a buffer here. Our cheapest and easiest buffer is just an inverter. And also this node we don't want to load down because this affects our delays. You can see that we have a delay here through this inverter back, and that's an important part of our setup and hold times. So we have another buffer here. Buffer, keep, I'll call that a keeper, and a keeper circuit. All right, if we look at the waveforms, I'm going to label these waveforms. This is node A. Okay, so we have D, we have node A, we have node X. We'll put boxes around these so we can know which ones we're talking about. Here's node X. Here's node B. This one also doesn't have a name, so I'm going to call this node C. And then this one is Q bar. Of course, we have another inverter here, but that's what we have. What I did is I went ahead and started up a clock signal. All right, so we have a phi signal. Some random waveform for our D. Okay, D is an input. So clock and D are not really necessarily tied together, although this, we want this to be in a synchronous circuit. We notice that in this circuit D and A is always the inverted of A, and there's a delay. The inverter delay. This inverter delay has two parameters to it. We call it TC. TC what? What's my name? TCD. The contamination delay, which is the minimum value, and then we have TPD. In Weston Harris book, this is our terminology. Contamination delay, propagation delay. Maybe the rise is different than the fall. If this is a more complex gate, we know that we have a spread of rise and fall times. Contamination and propagation is just the minimum and the maximum of those delays from here to here. Those are the simple delays. We have a delay here, contamination and propagation delay at this inverter, contamination and propagation delay at this inverter as well. And we see that happening in this circuit. We have D changes, A changes. It always changes. This is our contamination and propagation delay. We also have a contamination and propagation delay here. D changes, A changes. D to A, always. That's the only coupling between here. D changes, A changes. All right, remember that this A, we have A and X. You see this green arrow here. So this is green. This is our negative latch. So when clock is low, we are in track mode. When clock is high, we're in hold mode. This is what it means to be a negative latch. Okay. Track, hold, track, hold, track, hold, track, hold. It just follows the mode of the clock phases. All right, so when we're in hold mode, X doesn't change. X doesn't change, X doesn't change, doesn't change. You notice that A changed, but X does not change. The only time that X changes is when we're in track mode. Track mode has one event. We see that A changed, and right before the clock, it settled down, so A is low. We transition to track mode, and then we have a delay here from the clock to Q, we might call this, or node X in this specific circuit, where the output tracks goes from the clock and goes here. We call this the clock to Q delay. The minimum time is the contamination delay. We have this propagation delay, which is clock to Q. Do you see our terminology here? It's clock to Q. We have propagation and contamination delay. Remember, contamination is the shortest time, propagation is the longest time in this scheme. Remember, between node X and node B is just an inverter. It's pretty boring. X to B, inverter delay, X to B, inverter delay. Okay. The next event that we have going on is B. All right. Remember, we have B and C. This is on the input and the output side of our latch. Now, this is a positive latch. And I'll notate this here, positive latch. Okay. Positive latch, we're in hold, track, hold. Nothing's really happening because our input never changed. Here, we're in hold mode. Our B goes up. Our B goes up because of other causes. But since we're in hold mode, C does not change. C stays held at 0. That's what latches do. At this moment, we have a clock event, which is way up here. Okay. So now we're going to transfer this high to the output. Now that that switch gets closed, when we go to hold mode, remember it's a switch that closes. That delay is the clock to Q delay for the latch. Contamination and propagation is just the minimum and the maximum. Clock to Q delay, that's this time. Clock to Q. Remember, between C and Q bar, in our schematic, I won't make you dizzy, but that's just an inverter. Okay, that's another inverter delay. It's pretty boring. Next thing that happens that's interesting is we have D to A. All right, that's just an inverter. A changes, but remember, we're in track mode. Our clock is low. A and X is our first latch. It's our negative latch. So now we have A goes high, X goes high, because remember, this is a closed switch. The switch's contacts are closed. There is a delay here. Do you notice, if you look really carefully, I even drew this with a super slight delay. This is an RC delay. That switch, this switch has a resistance. That transmission gate's got resistance. There's a capacitor at the output node, or rather at X right now, and we have a RC delay there. It's a short one, but it's still there. We call that the D to Q delay. D to Q delay, contamination is the minimum, propagation is the max. So this is D to Q delay for a latch. There's they always go the same direction because it tracks. Right, and then there's an inverter here. We have an inverter here. So we have a chain of events. We have an inverter delay, we have a D to Q delay, and then we have another inverter delay to get to node B. As soon as our clock rises, okay, our second latch, our second positive latch, was in hold mode, so nothing was changing on the output. You see that right here. Then we go clock to Q delay. Our B changed. Our B was done changing before the clock event happened. So we were done changing. Clock event happened. That's this clock event here. Everything's on a grid. And then we go from clock to Q. That's the delay for that latch. Of course, an inverter to get to our Q bar, and now is here. So we start from here. Our D went low. It tracked through here through our first latch, and then when we have a rising edge of the clock, it finally makes it all the way to Q bar. Okay, so we have D changes, we have a clock event, and then that event propagates all the way down to our output here. Okay, the final thing, I've got one more example, is What happens when our timing gets really, really close? This is this one situation, this is the next situation. It's really the same situation. Well, it's the opposite. Okay. All right, so our D changes. Our D was low, it goes high. Okay, this is before a clock, so we're safe. We have an inverter delay. We are in track mode at this moment for this first latch, so we have a D to Q delay. Okay. We have an inverter, just a normal inverter. And then at this clock event, we have a clock to Q. But remember, this node here, node B, just barely got done changing, barely beat the clock. So what gets captured is this gets tracked here. Okay, so when we go from track to hold, this node X is going to quit changing. Here to here, this connection is going to be broken between A and X. But we barely got it in before we went to hold mode, and then propagate through again, and we got down to C, and of course another inverter here, another inverter delay. That's all this is. The time from D to clock, okay, the minimum time, okay, I'm going to put D to clock, D to clock. This is not an event. I should take the arrow off of here. This is not an event. D does not make the clock happen, but D needs to happen before the clock. It needs to be this direction. Otherwise, we don't get our Q to happen properly. Otherwise, we don't capture all of this edge. The minimum time, the closest that this D edge can be to the clock, rising edge in this case, we call the setup time. Setup time is a minimum time. All these other T's are measured times. T setup time is a boundary. That's an important thing to remember. Okay, if you want to see more of this, more of these definitions, where the definition table is, you can see Weston Harris 10.2.1. The tables and the figures are great. They're on page 378 and 379. I really want you to look at not just my handout in the video, but also study the figures in the book, because they're typeset and give you a different view of the same parameters. Thanks for watching for today.